Let's have a closer look at Moore's circle. We are comparing the element in the plate under biaxial stresses and Moore's circle. The variable phi is the inclination angle of the plane, that is the virtual plane. In the circle, when 2 phi changes from 0 to 2 pi, phi varies from 0 to pi. Phi varies from 0 to pi. When phi varies from pi over 2, 90 degrees, to pi, 180 degrees, the stresses are sigma n and tau, which leads to the expression for complementary stress at phi continuously changes from pi over 2 to pi. The left half of Moore's circle, Moore's stress circle corresponds to the complementary stress. The translation conveys the relationship between the angle phi and its double in the context of stresses sigma n and tau, and the connection to complementary stress on Moore's circle, particularly noting that the lower half of the circle represents complementary stress. This part corresponds to complementary stress. It is clear for you to understand that the segment OE is a normal stress. Sigma corresponds OE, okay, OE. This OE from this point to this is a normal stress. Sigma corresponds to the angle 2 phi, and DE, this length, corresponds to the shear stress tau corresponding to the same angle. In this slide, let us compare some points shown on Moore's circle with the inclination angles, as well as the normal and shear stresses acting on the corresponding virtual planes. Look at the point A on Moore's circle. At this point, 2 phi equals 0. 2 phi starts from this point, therefore 2 pi equals 0 at this point. And this point corresponds to the plane perpendicular to the x-axis. That means the virtual plane is oriented to the same direction as the positive direction of x-axis. On this plane, we can see from Moore's circle that sigma equals sigma x, and tau equals 0. Next, look at the point F. At this point, 2 phi equals pi over 2, 90 degrees. Therefore, phi equals pi over 4, 45 degrees. That corresponds to the plane as shown in this left figure. Phi equals 45 degrees. And on this plane, we can see that sigma equals sigma x. Sigma equals sigma x plus sigma y divided by 2. That is the average stress. And tau becomes maximum. That is sigma x minus sigma y divided by 2. So at the center, we find that tau becomes maximum by looking at this circle. And finally, look at the point B on the circle. At this point, 2 phi equals pi. 2 phi equals pi here. That corresponds to the plane perpendicular to y-axis, like this figure. On this plane, we can see that sigma equals sigma y, and tau equals 0. Tau equals 0 again. Here is an example problem concerning Mohr's circle. The question is, construct Mohr's circle for the case of biaxial stress of a thin plate where sigma y equals minus sigma x. So sigma y is the negative sign of sigma x as shown in this figure, right? In y direction, a compression stress is given, and on x direction, tensile stress is given. Okay, so for this special case, let's draw the Mohr's circle, right? Look at the figure, this. Okay, you can calculate sigma average by this formula, and substituting sigma y equals minus sigma x, we find that the average stress equals 0. And tau max, that is the radius of the circle, now becomes sigma x itself. Thus, Mohr's circle will be like this. The center is 0, origin of sigma tau plane, and the radius is sigma x. This is the answer. From this slide, we are going to study a special biaxial stress state called pure shear. Pure shear is a state in which the stresses in perpendicular directions have the same magnitude but opposite signs. This is exactly the same case as the example problem given in the previous slide. That means sigma x equals minus sigma y. Let us study the case in which sigma y equals minus sigma x in this figure. I am showing the formulas of sigma n and tau as the function of phi. By substituting sigma y equals minus sigma x into sigma n, we obtain sigma n equals sigma x cosine 2 phi, and tau equals sigma x sine 2 phi. Mohr's circle in this case becomes as this figure B. If phi equals 45 degrees, 2 phi becomes 90 degrees, then we obtain sigma n equals 0, 90 degrees, sigma n equals 0, and tau becomes tau max here, that is sigma x. This means that if we consider a square element ABCD oriented at 45 degrees in the plate, and the biaxial state sigma y equals minus sigma x as shown in the left figure, 45 degrees, okay, there is no normal stress on the virtual plane. On the virtual plane, there's no normal stress existing, and the shear stress tau becomes maximum as tau equals tau max equals sigma x. So the shear stress is the same as sigma y in the magnitude. The stress state of this element, ABCD, is shown graphically in the right figure C. This stress state is called pure shear. Okay? On this element only the shear stresses exist on each plane, like this. And with these forces, stresses, this element is deformed like the rhombus-shaped element shown in broken lines, A prime, B prime, C prime, D prime, like this. Then the original angle of C or A, originally 90 degrees, becomes like this. It is reduced a little bit. The angle, corner angle A, is reduced to be pi over 2 minus gamma. Gamma is the reduction angle that is usually small when we consider a small deformation. This stress state is called pure shear. In this slide, we study the strain related to pure shear. This is the element in the pure shear state. This element shown in solid lines, oriented at 45 degrees as shown in the previous slide. And the applied shear stress is tau. The square element is deformed into a rhombus shape as shown here, shown in broken lines, A prime, C prime, B prime, D prime. The corner point A moves outward to A prime, B moves outward to B prime, C moves downward to C prime, and D moves upward to D prime. Accordingly, the original corner angle of pi over 2 at the point A changes to pi over 2 minus gamma. If we redraw this element so that one of its edges coincides with the horizontal direction, it becomes like this figure. The deformation of the rhombus can be seen approximately as such a deformation of a parallelogram. Okay, this. Then it looks that the original corners C and A moves to C prime and A prime on the same line. The reduction angle gamma of the corner angle at A after the deformation becomes this angle in the bottom figure, this angle, right? From this we find gamma is approximately equal to tangent gamma. Gamma is almost the same as tangent gamma, and tangent gamma is AC prime CC prime divided by BC, and is delta divided by L. Delta is the distance between C and C prime. In this slide, we discuss the relationship between the shear stress and the normal strains, epsilon x, epsilon y, and epsilon z. First, the change in the angle gamma at the corner of the rhombus-shaped element shown in the previous slide is proportional to the shear stress tau. Conversely, tau can be considered proportional to gamma as well. Therefore, we can write tau equals g gamma, where g is the constant of proportionality, which is called modulus of elasticity in shear, or simply the shear modulus. From the relationship between the strain and the stress in biaxial stress state, we observe this: epsilon x equals sigma x divided by Young's modulus, and this is the effect caused by the stress in the same direction as epsilon x. And also, in this case, we have sigma y, that is the direct stress in the perpendicular direction to x axis, and the direct strain caused by sigma y divided by E also affects the deformation in x direction. And when sigma y is in tensile state, shrinkage is observed, and we assume that the strain caused by the perpendicular direction's tensile stress is proportional, and proportionality, coefficient of proportionality, is Poisson's ratio. Also, epsilon y equals sigma y divided by E minus the effect from the x direction. And in z direction, although there's no direct stress sigma z in z direction, we have the shrinkage caused by sigma x and sigma y, just like this. Okay. And by substituting sigma x equals minus sigma y, and in this case, because this is the case we consider pure shear, sigma x is the same as tau, and substituting this into the previous expression, no, not previous, this expression, we obtain these results. And the unit volume change, the volume change becomes epsilon x plus epsilon y plus epsilon z. So by adding this and this and this together, we find that the volume change, there's no volume change in this case. In this slide, we are going to derive the relationship between the shear modulus G and Young's modulus E. Look at this rhombus-shaped element previously shown. The shape in the solid line is the shape before deformation, while the shape in broken line is the shape after deformation. Because in x direction, the lengths OA and OC have changed to the lengths OA prime and OC prime due to the stress in x direction. The strain in x direction is epsilon x. Therefore, the length OA prime equals OA times 1 plus epsilon x equals OA times 1 plus tau over E times 1 plus mu, Poisson's ratio. Also, we observe OC prime equals like this. Okay? Then look at the right triangle, C prime O A prime, C prime O A prime, this triangle. Then tangent OA prime C prime, tangent OA prime C prime equals tangent pi over 4 minus gamma divided by 2. Okay, this tangent becomes this, and that can be calculated by the length of OA prime and OC prime. and OA prime is this, and OC prime is this. Therefore, it becomes like this. And by using this formula of trigonometric functions, we can convert this formula, we can convert this value like this, and this becomes this. Okay? And we use that tangent gamma over 2 is approximately the same as gamma over 2 when gamma is very small. All right? Therefore, gamma over 2 finally becomes tau over e times 1 plus mu. And from this, we obtain this. All right? Therefore, by comparing the coefficients, we finally find G equals E over 2 times 1 plus Poisson's ratio. And this is a relationship between the shear modulus and Young's modulus. All right? And this is worth memorizing. This slide shows a problem you have to solve by yourself. This explains how the volumetric strain epsilon v equals delta v, that is a change in volume divided by v, is derived using the direct strains epsilon 1, epsilon 2, and epsilon 3. That is, epsilon v equals delta v over v approximately equals epsilon 1 plus epsilon 2 plus epsilon 3. Derive this. This slide explains residual stress, which is initially hidden within the structure. Let us consider a straight bar of a certain length L equals L plus lambda. Once it is compressed so that its length becomes L, the bar experiences an initial strain of epsilon equals minus sine of lambda over L. Okay, and you are dividing the shrinkage with respect to this width, and we have to keep in mind that this shrinkage is rather small compared with this distance L. So this strain is called residual strain that exists in this structure, and you can't you don't know that this original strain, residual strain, exists from the observation. Therefore, when the bar is inserted between rigid walls as shown in this figure, it already possesses an initial strain from the beginning in this case. This strain causes an inherent stress that is not apparent from visible deformation and is called residual stress or initial stress. In this slide, we study thermal stress, that is a sort of initial stress. When a solid experiences an increase in temperature, it is expanded. The rate of the expansion per unit length depends on the choice of material, but is approximated to be proportional to the temperature increase. Let, for example, such a straight bar is supposed to be fixed between these rigid walls at the temperature T0. The temperature will then be increased to T. Let us consider this problem. In the free atmosphere, the elongation of the bar can be expressed as delta L equals alpha L T minus T0. This is the case when there's no rigid wall fixing. And epsilon T, that is the thermal strain, that is called thermal strain, is delta L divided by L divided by L. So alpha T minus T0 is this strain. And alpha is called coefficient of thermal expansion or linear thermal expansion coefficient. So in this, keeping this in mind, let's consider the bar may experience a temperature change from T0 to T. If the bar is not fixed and left in the atmosphere, it can expand freely in all directions. However, because in this case the bar is fixed between the rigid walls and the change in the length is kept unchanged. So we can easily understand if T is greater than T0, the bar tries to expand, but in order that the bar length is kept unchanged, the bar should be compressed from both sides. This amount of force per unit area is the thermal stress. In this case, the initial strain related to shortening the bar is negative. The thermal stress that exists in the bar to keep the length unchanged is obtained as this, and you have to multiply Young's modulus with the strain, so you obtain this.